everyone around the world. Thank you for taking a little bit of time out of your day to learn about controlling energy storage and distributed energy resources behind the meter. As Salil said, I come with 28 years of product development experience. Most of that time has been focused on developing appliance and solutions for commercial and industrial applications. That's what this is when we're talking about these controllers. We need them to work reliably and for years on end. I'm very proud of the teams that I've worked with and the products that I've helped to deliver into the market. Currently, I'm leading the energy management systems development team at Nuvation. This is the first of a three-part tutorial. Please go to nuvationenergy.com to learn about the other two tutorials that will be coming over the next several weeks, and you're welcome to register there. Today we'll give you an introduction to Nuvation Energy and some of the solutions we bring to the market. And we will then dig into the distributed energy resources, understanding how they fit into the energy distribution market. We'll talk about energy management and prioritization and control of these resources. And we'll talk about some of the applications, including demand charge management. And then we can take some questions and answers at the end. You'll notice on the slides a number of pictures. These are applications that Nuvation Energy has been involved in distributions around the world. Nuvation Energy, it was founded based in the electronic engineering design services as a company about 23 years ago. We've done over 1,000 projects for custom applications for services for other companies and people. About a decade ago, we formed Nuvation Energy to focus on the energy battery storage market and bringing solutions to that world. We'll talk about a number of those solutions over the next little while. We have two main offices, the Sunnyvale office in California, United States, and the Waterloo office is in Ontario, Canada. As I said, for the Nuvation Energy, we've got a number of installations around the world. Some are island applications, some are grid, and some are just specific buildings to meet certain industrial needs. Many of these sites have custom controllers that Nuvation has provided to provide the energy management and site controller integration aspects. Our battery management system is the foundation of the Nuvation product line. This was first launched about 10 years ago. Since then, we have integrated it with many different types of battery technology, with many different manufacturers in many different applications. Nuvation is the first BMS, configurable BMS, to receive UL 1973 and 9540 recognized product status. This is a very unique position for us. It's reconfigurable, which allows the higher end control systems to operate without having to deal with the details of the different battery technologies. They don't even need to know necessarily what they are. Our battery management system comes in multiple layers. We have the cell level and stack level controllers. This includes all of the functional safety aspects. around controlling batteries. Then at the higher level, we have a battery control panel. This allows operating the battery as a set of battery stacks as a single battery unit. Provides a common interface for control systems. It aggregates all of the data. It includes things like local data logging and functional status integration and things like that. A recent addition to our formal product lines is our End Controller EMS. This was just announced recently. This is a site controller and energy management system for managing distributed energy resources. We can do things like demand charge management, or it can take pass that responsibility up the chain to a higher level controller and respond to those inputs. We'll talk more about that as the presentation goes on. This rounds out our set of products to address many applications in the energy management, battery storage market space. From the top energy management system, site controllers down to individual cell. This integrated package allows good diagnostics and data reporting all the way up the chain. But our site controller does not need to integrate with our BMS. It can also integrate with other DER resources and battery management systems. Let's get an understanding of what we mean by in front of the meter and behind the meter. In the traditional power generation system, we have centralized generation resources. They provide the energy for the demand side, the customers, and the commercial and industrial applications. The customers are behind the meter from the perspective of the supply chain. In the supply chain, there's also entities dealing with transmission and distribution. This market has been evolving over time. Today, there's a lot more to it than just large single entity generation. We have things like solar, we have things like wind, we have batteries being integrated into the systems. It's now less expensive to provide energy with solar and batteries, combined with batteries, than it is to build even gas peaker plants. So the industry is changing very quickly. And then on the demand side, the customer side, they are also taking steps to install distributed energy resources such as solar panels and windmills and batteries and battery electric vehicles, charging stations. A lot of this is done today to avoid costs of buying energy from the grid. The whole grid right now is the investments are all focused around peak power because we need to have enough supply to satisfy all of the demand loads. Otherwise, parts of the grid need to shut down, or you have things like rolling blackouts. These distributed energy resources so far are dealing mostly with avoiding costs of connecting to the grid and dealing with peak reduction. A major announcement that just came out last month from the Federal Energy Regulatory Commission is FERC Order 2222. This is opening the door for a lot of innovation to come over the next several years, as people will now be able to feed in electricity from behind the meter in their distributed energy resources, feed that back onto the grid as an equal partner to the centralized power generation sources. So the RTOs and ISOs have a year to come up with their implementation rate structures and those details for how they're going to implement this order to allow people to feed energy back onto the grid. So as you're creating, investing in your distributed energy resources, keep this in mind as an alternative way to get some return on investment for your resources. Chairman Chatterjee, he came out with the quote about like Voltron, where all these different characters come together to form Voltron. This is the analogy of these DER aggregators will be able to take energy from a whole bunch of different distributed energy resources and coordinate the activity to fulfill the need of applications on the grid, such as voltage support, frequency regulation, demand charge management, peak reduction, things that peaker plants currently do today. Over the next decade, the US expects to see 19 million EVs on the road. This will be a huge amount of storage, larger than what we currently have. And when these can be coordinated together with these aggregators, it will create some very interesting business opportunities and solutions for solving some of these energy management solutions for grid energy distribution. Things are changing even without this FERC 2222 order. You can see over the last 10 years, solar installations have grown from 16 gigawatts up to 105 gigawatts. This acceleration is expected to continue to grow even faster. So the energy distribution of tomorrow is going to be behind the meters participating in the supply side as well. Let's dig in and understand a little bit more about distributed energy resource applications and why you might want to implement these and what a controller will be needing to do with them. From this table shows a number of applications. Many sites, many commercial industrial sites may have custom needs specific to their application, but often they can be categorized in some of these groupings. For example, backup power, basically providing an uninterruptible power supply for the site might be required. Demand charge management and peak shaving, this is all about reducing the peak demand, the maximum power that your site pulls from the grid, because often your energy costs are dictated based on what your peak demand is. So if you can use generation of energy or energy storage system to feed some of that peak to lop it off, you can save yourself a lot of energy costs. The future solutions around aggregator participation would also fit in this line here. You need a controller that has access to meter information for what your site is using and what it's feeding back onto the grid. Time of use and load shifting, you're not going to make a lot of money on this on its own, but if you combine this with solar generation or even wind, or you combine it with EV fast charging, you open up more opportunities to offset more of your grid usage and use your local resources, or to enable EV fast charging so people can charge the car in minutes instead of hours. When you're considering storage for your distributed energy resources, you need to make sure to keep in mind the ratings and storage capacity and how long you want this energy system to last. This picture here is of a portable power system that Nuvation was involved with that's used in the oil and gas exploration sites. This system uses a diesel generator along with a hybrid battery system to provide, the battery provides 120 kilowatt hours of storage and with 2C rating of power, so that's 240 kilowatts of power. And what they use this for is for peak shaving and voltage frequency stability at the site. By combining this battery with the genset, they were able to half the amount of fuel consumption by the genset, and they were able to double the life of the generator. So this is a very economical investment in battery technology to improve the capabilities of this application. So what's the difference between power and energy? So power is your instantaneous ability to do work. This will be dictated by the size of the PCS, power conversion system, that is part of the energy storage system. Oftentimes, it will be related to the voltage or number of battery cells that you have in series. Energy capacity is how long you can provide that ability to do work. So to last longer, you'll need to have more batteries involved in the system, more stacks, more things in parallel, so that it can last longer. This battery system is a lead acid battery system installed on an island in the Kingdom of Tonga. The lead acid is still commonly used in industry because of the experience of local technicians and in places where space is not constrained. So this island, they had a chance to use more space, so they used it. Nuvation replaced the BMS in the system, and because the old one wasn't working well, and made a much more reliable power system for the island. The other thing to pay attention to is the cycle life of the battery. Not all battery chemistries like to be treated the same way, and they will have different life expectancies. So pay attention to that as you're choosing your energy storage system, as well as setting up your control system. This application here is a battery backup system that Nuvation managed the installation of for a wastewater treatment plant in Santa Rosa. So this system provided basically a huge UPS, a lot bigger than the ones you see in your house. This one's capable of 2 megawatts of power for 15 minutes. So if you take 2 megawatts and divide it by 4, that gives you around 500 kilowatts hours of energy that you need to have in the system. That's how these two numbers relate here. For an energy management system, often it collects a lot of data in order to make decisions. This is a capture of a system running in the Nuvation Energy Lab. Our controller has a capability to log many bits of data into timescale database and then generate reports on those. So we'll work with, when setting up an application, we'll work with the application engineer to determine what information is required for that application. We'll dig into this graph a little bit more over the next couple of slides. The system that the controller is controlling here is a small system. It's 7 kilowatts of power. It only had about 32 kilowatt hours of storage available. And the power meter is monitoring the power for the whole Nuvation office in this case. The graph has a lot of details in it. So this slide here outlines some of the different bits of data that are available to the operator as they're looking at it. If you look at the top graph, that's dealing with the power, the instantaneous behavior of the system. And the bottom graph is showing the energy view, so what it's capable of doing in the future at any point in time. The graph shows, each graph has 2 lines on it that show set points. So the top line on the power graph is a set point representing the target peak power for the site. The line below it, the red line, is the target minimum power for the site. The blue shaded area is the power meter reading for the building, for the site. And then the orange is the power that's being either discharged or charged from the battery. And then in the bottom graph, similarly, we have 2 set points. One is for the minimum available energy for the site. And the other one is the minimum available storage at this particular time for the site. So we're showing storage as a space available for storing energy as a negative number on the graph, and space of the amount of energy that's available for discharging in orange as a positive number on this graph. So if we look at what's happening over this initial part of the system, we can see on the bottom, the energy graph, we have lots of storage available, and we have a little bit of energy available for discharge. The site power is shown here in the bottom orange line. So if the energy storage system wasn't available on the site, that's how much power would be drawn from the system. The blue line, the blue shading, which includes the part underneath the orange here, is what's being measured at the power meter. So the load was below the minimum set point, power set point for the site. So the controller used that available power to start charging the battery. And you can see the energy starting to be accumulated in the battery during this period of time. There is 4 peak power. So when the air conditioning or something else in the building came on, the demand for the building went above the peak power set point for as that was configured into the controller. So at this point, the controller recognized that by reading the power meter and said, oh, I need to start feeding in power from my storage to maintain this peak power setting for the set point for the site. This continued to charge the battery until the battery reached its set point for the minimum storage available. So hopefully that helps you understand what's going on the graph. Now we'll dig into what's happening at the tail end of the graph. So here we're going to see a demonstration of what happens when you have a mismatch in the power and energy requirements for the site in the energy storage system and in the configuration of the controller. So early on in this graph, you can see the power system. The controller is able to maintain this peak power set point by providing energy from the battery system. This continues, but around shortly after 8 a.m. in this graph, you can see blue lines starting to climb above the set point for the site. This is because the energy storage system was not able to provide the full amount of power to offset these peaks. So it did a best effort job to apply power from the battery to keep the peaks as small as it could. This continued until around 11 a.m. when the energy available for the application reached its set point. So the controller was no longer able to draw more energy from the battery based on the application settings. And this allowed larger peaks to go through the system. So if your energy billing was based on peak power, in this case, you would have to pay based on this peak at the very end, which is much higher than might have been possible with a different configuration of equipment. Some ways to mitigate this would be to use maybe different algorithms. So in this case, rather than an adjustment was made in the schedule to change the set points to bring the minimum storage available much lower. So this essentially told the controller that it should discharge the battery to free up space for more energy storage. Our controller was set to discharge at a fixed rate that was chosen by the technician who set up the system so that the battery would last long enough for the expected window. So it was able to shave off a couple kilowatts from every peak in the system. So you're guaranteed to have some savings. There's many other algorithms. For example, we could combine the two and provide peak saving based on the power limit as well as based on the energy limits, and change the choice of how that is done. So the short answer here is make sure you pay attention to your energy storage requirements based on the application, and pay attention to how you configure your ESS to meet those needs. Power smoothing or PV smoothing is another feature that our controller can do. This picture here is an application that's installed. It's in for a utility near Atlanta, Georgia. It's a 7 kilowatt hour battery that essentially is to smooth out the power rate of power change due to solar. So the blue line in this graph is showing what's happening with the solar collection. These dips in the blue line is when maybe a cloud goes in front of the solar panels, leading to a very quick reduction in the amount of power being generated. Fast changes to power demand on the grid causes instability. That's why the RTOs and ISOs have regulations around for limiting how quickly things change. So a controller can, with a battery, can slow things down if required. Battery electric vehicle applications. These require many controllers to work together to fulfill this application. The electric vehicle has its own controller that needs to be talked to. The site controller may need to coordinate the battery availability information. The site controller may need to, or the electric vehicle controller, charge controller may need to reach out to payment authorization systems offsite to get authorization to discharge energy. Anyways, the thing to pay attention to here is that local batteries can help enable fast charge applications, but having these batteries requires control systems to make them work. Here's another example of a system that Nuvation put in. This is a solar-powered resort off the coast of Panama. So Nuvation installed, set a BMS system to control the old batteries, as well as installed brand new batteries from a different supplier. This augmentation is typically a very tough problem. But for our control system, we use the same BMS with different configuration to control those two sets of batteries. And then we had a higher level controller that provided some custom dashboards for this application so they can see the information that they want to know. So in this case, the GSB batteries were the new batteries. They were the ones preferred to be used. They had a better cycle life and better capacity per stack. The Unity were the older batteries, so they were less preferred. And then the site also had a backup genset to charge the batteries in the case when the sun didn't provide enough energy to last for the full usage of the batteries. This custom dashboard, Nuvation designed it for the user. So it was a touch screen. They could easily drill in to see individual parts of the system, how well they were behaving. If there's any alerts or warnings that needed to be dealt with, and they could continue to drill in for more details. In this case, we had organized things in clusters. A cluster is a set of stacks to support 3 PCSs that work together to form 3-phase power for the island. The BMS, we had a site controller that took the information, the battery current limits from the BMS, and then modulated them to control which clusters were providing the power for the island. And we could continue to drill down for more information down to the stack level, or even for the individual cells if that was required for the application. So Nuvation has been a long time in the controller business. We focus on solving the problems that the application requires. This is another example dashboard for an installation in Norway. This installation has solar generation, it has storage, it has a commercial load, and it has a grid power connection. The controller is monitoring 3 power meters, inferring the 4th load. We get a high-level status of the site, quick view. You can identify that there's something that needs attention here. This site is also a set of string inverters to provide power. So there's 5 smaller inverters that are ganged together to provide the power for the site. In this case, one of the systems is disconnected, which led to a fault in the PCS. Again, we can provide the custom dashboards as required for your site. So a controller collects information from a whole bunch of different equipment. It makes decisions based on power meters, based on state of charge of the energy storage system. Maybe it's based on a schedule. Maybe it's based on other application-specific inputs. For example, going out to an open charge point service to get authorization. A lot of the times, this can all be done local without any external access or user intervention required. But sometimes a site may have layered control where an upper level control system makes the decisions on what's happening with the EMS. And maybe they get information from external systems or wherever they might need to get the information from. So controllers are set up so that they can, we set up our controllers for the application. We can allow multiple layers of architecture if required for very large sites. This is a potential architecture to support thousands of stacks or megawatts of many megawatts of power if needed for an application. So a controller may have a specific set of assets that it's managing and can feed up the information up the chain to where the decisions need to be made. Some of the different communication protocols that are commonly used in these energy management systems, Modbus RTU, Modbus TCP are very common. DNP3 are often used at the energy management system, the higher level control systems. Open charge point protocol might be required for EV vehicle integrations, battery charging. IEEE 1547 is often used in switchgear and grid power related equipment. So controllers can often need to interface with these and may have many other protocols they have to deal with for higher level control systems, depending on the application. So like I said earlier, Nuvation has recently announced the End Controller EMS. This is an implementation that is available for inclusion in projects for managing distributed energy resources. The controller can be customized for your site needs. Whatever applications needs to be done, we can find a way. We have lots of experience creating solutions for whatever the customer application needs to be from our electronic engineering design services days. And we can help with the integration as well. That concludes the information that I wanted to share with you. I hope that everybody was able to learn something new today and will be able to solve their problems better in the future. We have 2 more tutorials coming up over the next several weeks. You can join Michael Worry as he talks about battery warranty tracking, and Stefan Januin will be talking about battery state of health measurement and how that is done. I want to take this opportunity to thank Salil and PlugVolt for helping to organize this presentation. And I truly hope that everybody is well and has been able to learn something today. Now we will open the floor for some questions and answer period.